So I wanted to do one more module on the general material for Chapter 7. And then as I mentioned in the second lecture that I post this week, we'll go over some specific homework problems. So the first thing that I wanted to review for you is this idea of Varganon's theorem, because oftentimes when you take a statics class, people will ask you, oh, did you go over Varganon's theorem? And really, I think it's just because it has a fancy name. There's really nothing to it. And of course, in a statics class, you wouldn't prove it. But if you look at what this is really showing, just always focus on the equations first. If you didn't know that this was a cross product, if you didn't know these were vectors, if I showed these to someone that had never had calculus, they would say this looks a lot like distribution. And really think about what that means. Think about what's going over here on the right. Here, you would have to produce, in terms of what is shown, two different cross products. And hopefully what you learn from doing the actual cross product videos in the middle of this lecture is that cross products are generally a pain versus actually adding vectors themselves. So here on the left, you only have to compute one cross product. You add the vectors first. Here on the right, you have to compute individual cross products for each of the vectors. So what is this saying and why is it useful? What this is saying is if you have a system of forces acting upon a body, if you want to compute the moment of all of those forces about a particular point, one way you could do it is to compute each moment individually, right? That's what's going on here, R cross F1. That is the moment of force F1 about point O, since O is a position vector drawn from the origin O to the point of application of these forces A. You could do the same thing for force 2, you could do the same thing for force 3, and so on. And that way would require you to produce, in general, for this diagram, 4 different moments. You'd have to do 4 different cross products. However, the tendency of that force system to induce rotation about point O is going to be the same as a single force that is simply the resultant of those 4 forces. They're equivalent. So basically what you can do, rather than computing the moment of each of these individually, is to first add them all up, compute the resultant, and then compute the moment of that resultant. So that's basically what this says. You can compute a resultant first and then take the moment, or you can compute all the moments individually. They both are the same with respect to inducing motion on a body. And that's pretty intuitive to you. But if you read Varganon's theorem and it just sounds confusing, basically it's just telling you if you're trying to find the moment of a set of forces acting upon a body, you can just add all the forces together first, find the resultant, and then find the moment of that resultant. So I wanted to look at a bit of an example problem here. This is a pretty kind of similar to one of the problems that we worked beforehand, so we won't talk about it in too much detail, but we have a 100-pound force and it's being applied to the end of this lever that's attached to a shaft that's not shown at point O. And we know that the length of this actual lever is 24 inches. And again, the point of application of the force is 100 pounds. So we want to determine the moment about point O and then a bunch of other questions. So let's walk through these step by step before I actually show you the solution. So what is going to be the moment of this force about point O? Well, hopefully when you look at this, you immediately tell yourself that rather than doing a cross product, this is definitely something that you want to formulate using the scalar formulation. In the scalar formulation of moments, basically all that we need to do is to compute the perpendicular distance from the point about which we're computing the moment, in this case that's O, to the line of action of the force. So if we take this 100-pound force and we extend a vertical line of action all the way down, the perpendicular distance to a vertical line is just going to be the horizontal distance from O over to that line of action. So basically, if we were to take and draw a right triangle where the hypotenuse was 24 inches, this space is simply the elevation or the vertical difference between point O and point A. And this length is simply the horizontal distance. What you will find is that base length is simply the perpendicular distance from point O to the actual line of action of the force. So similar to what we did in the videos, drop down, extend your line of action, compute that perpendicular distance. What it's going to be is 24 times cos 60. That is the perpendicular distance multiplied by 100, and then just use your actual right-hand rule or your own intuition to see that that is going to cause an actual clockwise rotation. So by convention, that we refer to that as a negative moment. It's rotation about the negative z-axis if we have x and y-axis as being in the plane of this problem. For part B, the horizontal force at A that creates the same moment. So basically, if we were to pull this down, if we were to pull it to the right, well, notice if we pull it to the right and we extend that line of action out of that force, then the perpendicular distance from point O is just going to be the vertical elevation in that same triangle that we just computed. So we'll look at the actual diagram in a minute, but if we take 24 times sine 60, what that is going to give us is the vertical distance that you have to travel from O to go up to the elevation of A. Since a horizontal force would have a line of action that's at that elevation, it's going to be 24 times sine of 60. That's going to give us the perpendicular distance, and we're going to solve for the force needed to make the moments equivalent. So rather than confuse you, we'll go on and look at actually what's going on here. This is computing the actual actual moment of the original 100-pound force, about 0.0. As we mentioned, this is just the distance that you need to compute. You can get it as 24 times cos 60. They've extended their line of action out, computing that perpendicular distance. 24 cos 60 times 100 pounds gives us a moment of 1,200 pound inches, or pounds times inches. And of course, that is in the clockwise direction. It's easier to denote the actual kind of vector sense of this moment using clockwise or counterclockwise, as we discussed for two-dimensional cases. If we were to apply an unknown horizontal force and we wanted to yield the same moment, we would note that the perpendicular distance in this case isn't 24 cos 60, it's 24 sine 60. And if you take and multiply 24 sine 60 times this unknown force, you want to find what that unknown force needs to be 1,200 pound inches. That, again, is just the quantity that we received from the first slide. And if you compute that in the scalar sense, you get that it is 57.7 pounds. Now, it's asking you here, why must the direction be to the right? Well, clearly, if you want to induce rotation in the clockwise direction, you have to pull that thing to the right. If you pull it to the left, it's going to have the opposite sense of rotation there. So that's why it must be to the right. So the next question was, what is the smallest force at A that produces the same moment? Think about it and discuss with a neighbor. Well, if you have a neighbor next to you, feel free to, but if you don't, we'll just discuss it together. The basic ideal is that when we pulled purely in the vertical direction or purely in the horizontal direction, we weren't fully leveraging the actual lever arm or the perpendicular distance of this lever. So if you think about it, it's like when hopefully you've tried to loosen some kind of rusty bolt with a wrench before, right? You always want to pull at a perpendicular angle when you're doing that. And what that's allowing you to do is a perpendicular angle to the actual moment arm or lever here. What that's allowing you to do is to use this full 24 inches of mechanical advantage when you're trying to induce that rotation. So the first point to note is that the smallest force that you're going to be able to exert to induce the same moment as those other two situations that we looked at is going to fully use this 24 inches. It's not going to have that times cosine 60 or times cosine 60 or times sine of 60. It's just going to be 24. So what we're basically going to do is find out what force we can multiply by 24 to get the moment or the torque that we've looked at in the last two examples, which is 1,200 pound inches. And if you solve for that, what you'll find is you only have to exert 50 pounds of force if you fully use this 24-inch lever arm. But the thing to note is, in order to do that, you have to align the line of action of this force perpendicular to this the actual lever itself. And that's all that it's showing you there. And you can draw a diagram in front of you and see how that would actually orient in the XY plane. So see, what is the smallest force at A that produces the same moment? So we already talked about that one. So let me make sure that we're on the same thing. That's the one we just did. And then D, determine the point of an application of a 240-pound force to produce the same moment. Basically what they're saying is if you pulled 240 pounds in the downward direction, remember that when we pulled 100 pounds all the way out here at point A, we were able to induce a tendency of rotation that was described by the moment 1,200 pounds times inch. Now, if we actually were to move that closer in, right, to achieve the same tendency to induce rotation, we would have to increase the actual magnitude of the force. So they're basically asking you, if you increase the magnitude of the force to 200, if you actually doubled it, there we go. I'm sorry, it should be 240 pounds. If you increase the magnitude of the force from 100 pounds to 240 pounds, how close could you go in and induce the same effect? So in this case, basically what they're doing is we're trying to find the actual perpendicular distance along O at which we're applying this force. So what we don't know previously, it was just the entire length of this lever times the actual, remember to get this perpendicular distance here for a vertical force, that's going to be cosine 60. So it's basically this unknown distance D, which is just the distance from O to the point of application of the force, times the actual cos 60, and that is giving us the actual perpendicular distance of the lever arm here. We want that to be equal to 1,200 pounds times inches, knowing that we're going to allow the force to be 240 pounds. And if you solve this equation for D, what you find is that D is 5 inches in this case. So just to show you what's happening there, when we pulled at the end of the actual lever arm and we had the full 24 inches, we were able to only apply a 100-pound force to induce this much rotation. If we're able to apply 240 pounds of force, we're able to only pull on that lever 10 inches out from the actual point of rotation versus the entire 24 inches. And the last question just basically asks, hey, all of the forces that we considered in parts A through D of this problem, they all induce the same tendency of rotation about 0.0, 1,200 pounds times inches of rotation. And the question is, are they equivalent forces? And even though, are they an equivalent force system rather? And even though they're tending to induce the same rotation, the key point is they're not equivalent forces because the actual forces themselves are not the same. So this is kind of a complicated ideal. We can talk about it a little bit more when we look at the homework problems. But generally speaking, in order for a force system to be the same or to induce the same tendency of motion, both translation and rotation, the forces have to be the same, both the magnitude and the direction, and the couples have to be the same. And the key point is that in these different systems that we considered, both the magnitudes and the lines of the direction of the forces were different, so they're by definition not equivalent systems. So I know that's a lot for this week, but that's probably what we'll get through on the actual exam content that we'll look at next week. So for the second lecture of the week, we'll look at some more example problems from your homework, and then next week we'll review for the first exam.